very good morning and a warm welcome to the 7th lecture on the subject of digital signal processing and its applications. We will spend a few minutes in recalling what we did in the previous lectures. In the previous lectures, we were looking at what an LSI system is characterized by. So, we noted that for a linear shift invariant system, it is adequate for us to know what is called the impulse response or the response of that LSI system to a special chosen input, namely the unit impulse. Once we knew the output of an LSI system given a unit impulse input, we know everything about the system. In other words, we know what the output would be for any input. And in fact, we proved last time that the output, the input and the impulse response are related by an operation called convolution. The convolution of the input sequence with the impulse response sequence results in the output sequence. Convolution is an operation in its own right. What I mean by that is, independent of the fact that it is an important operation in the context of linear shift invariant systems, convolution can be thought of as an operation between two sequences, irrespective of where the two sequences come from. In fact, there are reasons why we may want to think of convolution in that manner. And let us take a couple of situations where we need to deal with convolution as an operation independent of the context of LSI systems. In fact, let us take a situation where we have cascaded two LSI systems. So, let us consider a situation where we have an input x of n being applied to one LSI system, let us call it S1, with impulse response H1n, the output of which goes to a second LSI system. Let us give it the name, give it the name S2, and here the impulse response is H2n, and this results in the output yn. This is called a cascade interconnection, a cascade or a series connection of two LSI systems. Now, it is obvious that if we use the symbol star to denote convolution, then y of n is equal to first xn convolved with H1n and the resultant convolved with H2n. So, here we have two convolution operations following one another to relate the input to the output. And there are several questions that we can ask. One question is, what would happen if I interchange the order of these systems? So, if I were to interchange S2 with S1, would it yield something different, right? The other question that we need to ask is, can I replace this combination, this cascade combination by one single LSI system, right? So, let us put these two questions down. Question 1, what would happen if I interchanged S1 and S2? And question 2, is there one system, let us call it S, which can replace S1 and S2 equivalently? Now, we will answer the second question first. In fact, the answer to the second question would emerge from trying to find out whether I can change the location of the bracket. You see, what I mean by that is, suppose it were to be true that means I could replace S1 and S2 in cascade by a single system S, perhaps with impulse response Hn. Obviously, the output would be Xn convolved with Hn, isn't it? And we need to find out this Hn. And what do we actually have Yn to be? Actually, Yn is Xn convolved with H1n followed by a convolution with H2n. So, my difficulty is the place where the bracket lies. We shall show now that this is equal to Xn convolved with H1n convolved with H2n. In other words, we can change the position of the bracket for convolution. Is that correct? We shall prove this. This is what we shall now prove. And this property is called the property of associativity. So, now we are looking at convolution in its own right, associativity of convolution, right. So, in general, what we need to show is that Xn convolved with H1n, and here we do not necessarily imply Xn, H1n or H2n to be inputs or impulse responses. They are any sequences really. Now, let us take the left hand side. I shall indicate to you the modus operandi of the proof, and I shall leave some steps of the proof to you to complete. Is that right? So, the modus operandi of the proof, or the method, the process to be followed to prove this is as follows. Consider the left hand side. Now, Xn convolved with H1n can of course be written as summation on all k xk Hn minus H1n minus k, okay. All right. Now, essentially this is a function of n, okay. This is not the whole left hand side, I mean this is just a part of it. So, I am just so we are processing the left hand side. That is what I mean by putting this double line here. This is not done, we have just written one part of the left hand side. Now, we will complete this. So, we have Xn convolved with H1n, further convolved with H2n to be summation on k. Now, you see here I need to bring in one more variable. So, I will not write n now. This is k, but here I need to introduce one more variable. Let us call it L. And we put a summation on L now from minus to plus infinity and H2 n minus L. Is that correct? So, this is the expression. This is the complete left hand side. Any doubts so far? Yes. Now, we write the right hand side. And the right hand side is of course xn convolved with h1n convolved with h2. And this is very clearly summation k running from minus to plus infinity xk, and I need to write, I'll use this to denote the sequence obtained by convolving h1 and h2. This sequence evaluated at n minus k. Is that right? Whatever that sequence be. Now, when you evaluate that sequence at n minus k, we know how to write the expression for the n minus kth sample of that sequence. We need to use a summation to write that sample as well. Okay, the n minus kth sample of the convolution can be obtained as follows. So, this is summation k running from minus to plus infinity xk, and then I need to put a bracket, and I need to have, let us say, an m running from minus to plus infinity h1m and h2 n minus k minus m, isn't it? I am evaluating the convolution at n minus k. Is that right? So, what I need to do is to now bring these two expressions together here. I have this expression for the right hand side and I have this expression for the left hand side here, and I need to compare them. Let us write them on the same page. With RHS, which is summation k running from minus to plus infinity, summation m running from minus to plus infinity, xk, h1m, h2n minus k minus m. And now it is very clear to us how to prove the equivalence of these two expressions. You see, what we really need to do is to make a substitution of variable here. If we replace the variable L minus k with the variable m, the summation on k is common to both. As far as the summation on L here is concerned, for any fixed k, remember the summation is from all k equal to minus to plus infinity. That means the summation is on all integers k and all integers L in the left hand side, and all integers k and all integers m on the right hand side. Is that right? And xk is the term common. Now, if we replace m for L minus k, then it is very clear that n minus L, what we need to do is to replace L. So, L is then m plus k, and of course, now it is very easy to see that n minus L would then become n minus m minus k. But the only thing we need to justify is that the summations are also correct, and that is very easy to see. You see, k is as it is, k runs independently from minus to plus infinity. The question is what happens to m. For any fixed k, when L runs over all the integers, m also runs over all the integers. So, m, which is L minus k here, runs over all the integers when L runs over all the integers, or vice versa. You see, for a fixed k, L and m would concurrently run over all the integers. Of course, not the same integer, but they would run over all the integers independently, and therefore, one can replace this summation, double summation on k and L over all the integers by the double summation on k and m also over all the integers. And therefore, the left hand and the right hand sides are equal, and that proves the property of associativity of convolution. Now, we need to spend a minute in ensuring that we have no doubts about this proof. Do we have any doubt about the proof? Because it is a very important conclusion that we have drawn. Is that right? So we have concluded that convolution is associative, and that answers our first question. Convolution is associative. This is a more general conclusion we have drawn. And of course, its implication for the context of LSI systems is that S indeed exists, the equivalence system exists, and that equivalence system has the impulse response H1 convolved with H2. Very interesting. Now, we need to answer the second question. The second question is, can I interchange the order? And that amounts to asking, you see, now in a way we have also got an interpretation. We know that together the impulse response of the equivalent system is H1 convolved with H2. And if you could interchange the order, then the impulse response will be H2 convolved with H1. So, in other words, we are asking whether convolution is commutative. In other words, would H1 convolved with H2 be equal to H2 convolved with H1? Now, please note that here I am abusing notation a little bit by suppressing the dependence on the integer index. I am just writing, and anyway, in a way it is not too much of an abuse, because ultimately convolution is an operation between sequences, not between numbers, isn't it? It is not too much of an abuse of notation. So, let us answer this question. Once again, let us look at the left hand side first. So, left hand side is essentially summation k running from minus to plus infinity h1 k h2 n minus k. And here again we make a very simple substitution. We substitute n minus k by L, and we note that k running from minus to plus infinity leads to L running from minus to plus infinity for fixed n. This is easy to see. For a fixed n, if k runs over all the integers, then n minus k, which is L, also runs over all the integers. And therefore, we can make a replacement here. We can replace n minus k by L, and that is very easily what we want on the right hand side. So, replace n minus k by L, which means k is n minus L, and of course, then we have summation L from minus to plus infinity h2 L h1n minus L, which is essentially the right hand side. And therefore, we have concluded that the left hand and the right hand sides are equal and convolution is commutative. Yes, there is a question, yes. Yes. So, I will repeat the question. The question is, you see, we said that in this case, for example, when k runs from minus to plus infinity, n minus k would invert, so to speak, or in other words, it would seem to run from plus infinity to minus infinity. Well, that is correct. I mean, what I am trying to say is, the set of integers, the entire set of integers is covered by k and it is also covered by L, though not necessarily in correspondence. That means, when k is at a particular integer, L is not the same integer, that is true, but there is a one-to-one correspondence. So, for every k there is a unique L, for every L there is a unique k, and not only that, the entire set is spanned. You know, when you are dealing with infinite sets, you have to be careful. So, in fact, the question has raised an important point. When you are dealing with infinite sets, one must be sure that the infinite sets are equivalent, and in infinite sets you cannot simply conclude they are the same unless you can draw a correspondence. That means you must be able to, if you claim that two infinite sets are the same, are equal, then you must be able to draw a one-to-one correspondence between those two sets. I must be able to make handshakes between the elements of the two sets, and here you can do that. You can make a handshake between elements of the set k and elements of the set L, a one-to-one handshake. So, of course, the handshake is not between the same elements, but between different elements. Is that clear? Is that clear? So, are there any other questions about this proof? So, you see, it's very important that we clarify questions as we go along, otherwise it would lead to gaps in understanding and weaknesses in foundation as we proceed, and a weak foundation leads to cracks on the upper stories or upper floors. Is that right? So, foundations must be strong, and then that does not allow cracks to seep in on the upper floors of a building. So, are there any other questions on the proof so far? Yes, is the proof very clear to everybody? So, what is our conclusion? The conclusion is that convolution is commutative. And in particular, what does it mean for LSI systems? The order of a pair of LSI systems in cascade can be interchanged. That answers question 1. Now, I leave it to you as an exercise to prove the following. Prove that we have, whenever we have multiple LSI systems in cascade, let us say n, capital N such systems in cascade, any interchange, any reordering is permissible. In other words, the order does not matter. If you have a set of LSI systems in cascade, not just two of them, any number of them, then any reordering of those LSI systems in cascade does not influence the overall input-output relationship. And to prove this, you shall require both commutativity and associativity of convolution. Is that right? So, please use commutativity and associativity to prove this by mathematical induction or any other method that you choose. Is that right? So, I leave this to you as an exercise. But now we have we've seen something very interesting. We can combine LSI systems in cascade. Of course, it's a minor variation or a very easy question to answer when we ask what happens to LSI systems in parallel. That's very easy to answer. So, suppose you have the same xn being given to two LSI systems in parallel with impulse responses h1n and h2n. By parallel, you mean you apply the same input and then add the outputs. The answer is very easy. Can we find an equivalent system for this? And if so, what is the equivalent system? Well, it's very easy to see. That y of n is equal to xn convolved with h1n plus xn convolved with h2n. And of course, this can be written as summation k over all k integer h1n minus k plus summation on k xk h2n minus k, which of course is very easy to combine. This does not require any great knowledge of, it's just a simple distributivity property of multiplication that we know very well, where hn is equal to h1n plus h2n. Very easy. So, in fact, when we have two LSI systems in parallel, there is an equivalent LSI system whose impulse response is the sum of the impulse responses of the individual LSI systems. Simple enough. So, now we are well in a position to deal with any combination of LSI systems in cascade or in parallel, or a combination of cascade and parallel. Is that right? We can always find an equivalent LSI system for them. The only problem is, if you wish to find an equivalent LSI system for a cascade, it's hard work because you have to do a very cumbersome operation, convolution. So, this is another reason why we might want to see if you can go to some other domain or go into some other mode where I can carry this operation out more easily. And in fact, it's quite beautiful how several questions in signal processing converge to one answer. Now, recall that the whole reason why we started discussing linear shift invariant systems was to deal with sinusoids. We come back to the same story again. There we had those sinusoids, we had complex exponentials because we did not want sinusoids, and the reason why we wanted complex exponentials was that although a change of amplitude could be represented as multiplication by a constant, changes of phase could not, but they could if you dealt with complex exponentials. And therefore, we asked what is the system which leaves a complex exponential as it is in frequency, but changes only the amplitude and phase, and we said that system must be LSI. Now, we need to justify that. So, why have we worked so hard to build all these properties of convolution unless we can show that we have indeed got where we wanted to. So, now let us ask the question, what happens when we feed a complex exponential of angular frequency omega? We will use small omega, and let me now bring in some notation here. So, what happens when we feed in a complex exponential of angular frequency omega into an LSI system, let us call it S with impulse response Hn. Now, a few remarks about the angular frequency omega. Henceforth, we are going to use what are called normalized periods and frequencies. And what we mean by that is that we shall assume that the sampling angular frequency, or well, let us first take the sampling frequency itself. We will take the sampling frequency to be 1 unit. You know, the unit is our choice ultimately, whatever it is. If it is 10 kilohertz, we will say 10 kilohertz is 1 unit. If it is 1 megahertz, we will say 1 megahertz is 1 unit. So, we will say the sampling frequency is 1 unit, is the unit frequency, whatever. So, you can always choose your unit, and therefore, of course, the sampling period is also 1 unit, obviously. It is the reciprocal of the frequency. Of course, these are units of different quantities. Sampling frequency has units of frequency, whatever they might be, and sampling periods have units of time. So, therefore, the sampling angular frequency becomes 2 pi times 1 unit. So, whenever we are dealing with a discrete system, we will assume that we have chosen the unit so that 1 unit is equal to the sampling frequency, and therefore, the sampling period is 1, and thereby we shall use small omega to denote what is called the normalized angular frequency. Or the angular frequency in these units. Now, we need to reflect for a minute what the unit of this normalized angular frequency would be. You see, when we normalize, we divide. So, for example, if you say you have normalized the angular, or you have normalized the frequency of sampling, you have actually divided the sampling frequency by the actual sampling frequency. So, for example, if your sampling frequency were 1 megahertz, you have divided all frequencies by 1 megahertz to get the normalized frequency. Similarly, if you have divided the angular frequency in a similar way to get the normalized quantity, then in fact what you have done is to replace radians per second. Radians per second was the unit of angular frequency as it were, but you have divided this by the sampling frequency in actual value. So, radians per second divided by per second or hertz leaves you with radians, and therefore, the units of normalized angular frequency here are radians, not radians per second. Similarly, the units of period or units of frequency are null, there are no units, okay, because you have divided hertz by hertz, they are just numbers. Yes, there is a question. Okay, so the question is it appropriate to think of this as a unit or to think of this as an angle? Well, both are correct. You see, what we are saying, in a way, what omega denotes is how much of angle is covered in a unit sample time, in a sample time. So, you see, when omega is equal to 2 pi, that means when you have used the sampling frequency itself, then you have covered an angle of 2 pi in a sample time, right. So, essentially omega is a measure of the angle covered in one sample time. That is another interpretation, yes, that is why the unit is radians. All right, then we will agree then to use the normalized angular frequency, because you see we are going to use the integer n to denote the sample number and also to denote the sample time, since the sampling time is unity. So, therefore, we have e raised to the power j omega n as the complex exponential, otherwise we would have to write down e raised to the power omega ts times n and so on, right. So, we do not need to do that now. So, when we feed e raised to the power j omega n to this LSI system S, with impulse response Hn, we know what we get out. We will get out e raised to the power j omega n convolved with Hn. Now, here we are going to invoke the commutativity of convolution, and that would give us Hn convolved with e raised to the power j omega n equally well from commutativity. Is that right? So, if we use that expression, then it gives us summation k going from minus to plus infinity hk e raised to the power j omega n minus k, and that is very easy to break up. It is k from minus to plus infinity hk e raised to the power j omega n e raised to the power minus j omega k. Now, note that here e raised to the power j omega n is independent of k. So, I can draw it out of the summation, and I am left then with an infinite summation on k. The infinite summation on k is in fact a function of omega and a function of h. So, let me denote this summation from k going from minus to plus infinity hk e raised to the power minus j omega k by capital H of omega. Whereupon what we have said essentially is that e raised to the power j omega n going into the system S with impulse response Hn has led to e raised to the power j omega n coming out, but multiplied by a complex constant capital H of omega. Please note that capital H of omega is a complex constant, but of course, at the moment we have kind of brushed something very important under the carpet. Let us look back at this expression here. H omega is summation k going from minus to plus infinity hk e raised to the power minus j omega k. There is an infinite summation here. Now, infinite summation is not guaranteed to converge. An infinite summation can diverge. In fact, this is a problem with convolution in general, and we had brushed this issue under the carpet even the last time. We had conveniently ignored that issue altogether. That is because we had dealt with finite length sequences. So, convergence was never an issue. But in case our sequences happen not to be of finite length, there could be a problem in the summation, whether it is in the context of convolution or it is in the context of this response that we see here. And we need to answer whether there is something that we should impose upon the system to make this summation convergent. Now, one thing is clear. If this summation converges, so let us see, if this summation converges, then we have a very interesting, in fact, we have done what we wanted to. When we given a complex exponential of frequency omega, angular frequency of normalized angular frequency omega to the system, what we get out is the same complex exponential, but multiplied by a complex constant. There is no other change. That means each complex exponential is dealt with in a decoupled way. So, now if I have a sum of complex exponentials, of course, it is a minor, it is a very simple thing to see that if I can multiply both sides by any complex number here. So, I can multiply, let me in fact rewrite this. So, if I take a times e raised to the power j omega n and give it to the same LSI system, I would of course get a h omega e raised to the power j omega n. A is any complex number. Provided h omega converges. That is the $1,000,000 question. When would it converge? But at least it's soothing to see that provided we have convergence, we have got what we wanted. If I have a linear combination of complex exponentials with different angular frequencies, what is going to emerge is the output to each of these complex exponentials treated independently, and the output to each of these complex exponentials is going to be the same complex exponential multiplied by an appropriate constant, which depends only on the angular frequency. Of course, it depends on the impulse response, but since the system is the same, the response is the same for that angular frequency. So, we have got where we wanted, with the only catch that we do not know when this would converge. Can we guarantee that this summation converges all the time? Now, to check convergence, let us explore the expression itself. In fact, convergence ultimately has to do with the magnitude. The phase is irrelevant. So, let us look at the magnitude of h omega. The magnitude of h omega is obviously the magnitude of h k e raised to the power minus j omega k. And this is obviously less than or equal to the sum of the magnitudes. That is, you see, the modulus of a plus b is always less than or equal to the modulus of a plus the modulus of b. And you can keep extending this to an infinite summation. So, this is less than equal to the modulus of h k times the modulus of e raised to the power minus j omega k. But of course, the modulus of e raised to the power minus j omega k is obviously 1, and therefore, the modulus of h omega is less than equal to summation k going from minus to plus infinity mod h k. So, we have what we clearly see is a sufficient condition The sufficient condition is that this is finite. So, it means if the impulse response sequence is absolutely summable means the sum of the absolute value of the samples is finite. If the impulse response is absolutely summable, then we shall make a remark. Then the output to a complex exponential of phasor converges for any angular frequency. You see, please note that this condition is sufficient. The way we proved it, we have only proved sufficiency, and in fact, it is indeed just sufficient. The fact that it is only sufficient is a very subtle point. We will understand that better later. But we need to appreciate the meaning of this condition a little better. Mathematically, of course, we see it. It is an absolute sum, it is a sum of absolute values. Yes, there is a question. Yes. So, the question is, in this page here, how did I conclude? No, what I am saying is, if I want, what I have shown is that mod h omega is less than or equal to this absolute sum here. So, I am saying a sufficient condition for this to converge is that this is finite. So, this is a sufficient condition. I am not saying that this is necessarily finite, but if this is finite, then this converges, that is what I am saying. So, as I was saying, we need to now answer what is the physical interpretation, what do we mean by this being absolutely summable. And in fact, we will get a hint if we only look at the general convolution expression once again. We shall do that and we shall carry on the discussion in this and the next lecture. So, let us take that LSI system with a general input. We have Xn, we have the same impulse response Hn, we are asking what does the fact that, and we of course we have been told that this is true given. So, of course, we know what Yn is. Of course, Yn is summation k from minus to plus infinity xk Hn minus k, but now you will agree with me that I can also write this down as hk xn minus k, because convolution is commutative. So, let us take the modulus of Yn. Modulus of Yn is the modulus of summation k going from minus to plus infinity hk xn minus k, and of course, this is less than or equal to summation k from minus to plus infinity mod hk mod xn minus k. As usual, because mod a plus b is less than or equal to mod a plus mod b. Now let us look back at this. You see here, suppose we manage to put a bound on this. Bound means we put a supremum on it. Supremum means we identify a finite non-negative number such that none of these magnitudes can be more than that number. In other words, let us assume that mod xn is less than or equal to some mx, where mx is a quantity greater than or equal to 0 for all n. In other words, the input is bounded. By mx. We say this is the terminology that we use. We say the input is bounded by mx. Obviously, the output is also bounded now. Mod Yn is clearly then less than or equal to mx times summation k going from minus to plus infinity mod hk. And if this is finite, the output is also bounded. And in fact, here too we have what is called a constructive proof, not just an existential proof. So, what we have shown is that if that condition, absolute summability of the impulse response, is satisfied, then a bounded input results in a bounded output. That is a serious conclusion. And not only have we concluded that, we have also shown what the output bound is. That is what I mean by constructive. You can calculate the output bound, or at least you can calculate one output bound from the input bound. Could be better. Now, this leads us to one more property that may or may not be possible in systems, in LSI systems, and that is called the property of stability. In fact, we define in the next lecture the idea of stability in terms of inputs and outputs being bounded. There are different notions of stability, and we shall talk more about these notions and the connection to the impulse response in the next lecture. Thank you.